Hello, everyone. Thank you for attending my poster presentation. This is Hanli Wu, a PhD student from Missouri University of Science and Technology. My advisors are Dr. Jenny Liu and Dr. Xiong Zhang. The topic I'm going to talk about is use of lightweight aggregate for air convection embankment in permafrost regions. The freeze and thaw of permafrost can cause many engineering problems such as soil settlement, snow cracking, pounding, and pavement deformation. The air convection embankment has been studied for many years. Previous studies have confirmed that ACE can be successfully used to protect roadway embankments in permafrost regions. Our recent study indicated that the cost benefit and cooling performance of the cellular concrete ACE was much better than the crushed rock ACE and the conventional salty sand gravel embankment. However, the impacts of lightweight aggregate on overall performance of pavement structure remains unclear. This research focuses on the following two aspects. The first one is to evaluate the thermal performance of the pavement structures with the selected interlayers. The second one is to evaluate the pavement responses and the fatigue failure of the hot mix asphalt layer and functional failure of subgrade soil. This section shows the cooling mechanism of the ACE. In numerical simulation, 6 cases include a typical Alaska pavement, a conventional salty sand gravel embankment, a crushed rock ACE, and 3 lightweight aggregate ACEs were investigated. The typical Alaska pavement was used as a reference to evaluate the performance of other 5 embankments. The pavement thermal analysis was conducted using temps and SS fluent. The pavement performance analysis was conducted using FlexPave and Alaska flexible pavement design software. This is material properties and boundary conditions used in temps. This slide showing the modeling procedure of the pavement structures using SS fluent. This is the geometry of in the numeric model. This is a table shows the pavement performance analysis inputs for FlexPave and Alaska flexible pavement design software. Let's use the cellular concrete ACE as an example. The open-graded cellular concrete turns the embankment into a very porous medium. The porous medium is full of air and the cellular concrete blocks. In winter, the ambient temperature was lower than the underlying permafrost. The lightweight warm air rises and the dense cold air falls. The air convection speeds up the heat transfer and cools down the soil. In summer, the ambient temperature is higher than the subgrade soil, and the pavement structure is mainly heated from the top surface. The air density gradient is relatively stable, which allows the porous medium to function as a thermal insulation layer to prevent the subgrade soil from thawing. The signal performance analysis indicated that the damage developed during summer in all seasons, all sections, was higher than during other seasons. The sections with interlayers filled with cellular concrete and lightweight expanded clay aggregate show the least amount of fatigue damage. Based on the result and discussion, we can get the following findings. Pavement structure with the proposed lightweight insulating layers could effectively reduce the temperature gradient of asphalt layer and thereby mitigating the thermal cracking. Using lightweight aggregate ACEs can significantly reduce the temperature variation of the ice-rich subgrade and reduce the risk of soil settlement of subgrade. However, using foam glass aggregate in pavement should be very cautious due to its relatively low resilient modulus. Cellular concrete aggregate and lightweight expanded clay aggregate interlayers could effectively reduce the fatigue damage and reduce by the differential soil settlement of the subgrade soil in hot seasons. Thank you very much for attending my presentation. If you have any questions, please feel free to contact me.